Good morning, and we're going to be talking today about section 4.1 and polynomial functions and their graphs. A while back we talked and focused heavily on polynomial functions back in chapter P, but we really haven't discussed it yet since then, and so we're going to do a little review here. Here on the left you have some examples of what polynomials are, and these ideas on the left are always going to be polynomials. Now let's look at some characteristics of these factors. You'll see each of them has an exponent that has an integer or an invisible integer 1, or not an integer at all in each of these other cases. Over here on the other side we've got some situations where we have an integer of -5 as an exponent, an integer of square root of x as an exponent, and an integer of 1/2 as an exponent. Each of these three issues are parts that are going to cause them not to be a polynomial. So on this side they are not a polynomial, whereas on the other side they are. Now there's some other characteristics of what might be a polynomial. Things that are okay to have there is you can have any kind of a number, a coefficient, in front of that, so long as that number is a real number. Over here you see this I value, that's the square root of -1, and you know that's not a real number, that's an imaginary number, and so that is the reason that this part over here is not a polynomial. Alright, well let's keep going down, and let's answer some questions. So what must be true of our exponents on the variable? Okay, our exponents must be what? Let's just think for a second as we look back up. Our exponents must be integers. Alright, can they be anything else? An integer, remember, can be negative or positive. So can they be integers? Let's think about that for a second. Well, in reality is they cannot be integers. Okay, they must be whole numbers. And let's kind of go from there. In other words, they can be 0, 1, 2, all the way up. So we're holding at 0 and we're going all the way up in terms of that set. They cannot be negative numbers. Alright, now let's look at our next question. What's true of the coefficients in front of each variable? Okay, any real number can be there, but not imaginary. Okay, so we've got some good guidelines for what is going to make us to have polynomials and what is not going to have us to be polynomials there. Just looking for integers or just constants. Obviously this is an x to the 0, and that's why that is a whole number there as we're looking through. Moving down, we need to remember some of our unique names of our polynomials. These first three are what you are probably most common with: constant, linear, and quadratic as our possibilities. And examples of that, very simply, are going to be 3, 3x, or 3x squared. And in each case, we're talking about the exponent of our problem. It has absolutely nothing to do with what goes behind the number, but it's the highest degree on the problem. Now, cubic, as you would imagine, has a degree of 3. So if we describe a cubic function, we have 4x cubed plus anything, plus anything, plus anything, plus anything. And obviously these are also plus or minuses. So long as these numbers are x squared, x, and constants and things like that, that's not going to be an issue. And in reality it looks like I should not have done that last one there, because as we're going down, that's not going to be the case. Our next idea is quartic. Quartic is degree of 4, and then quintic is degree of 5. Sometimes we may refer to these just as 4th or 5th degrees, as the words quartic and quintic are very rarely used, but we will be talking about them basically in some cases. But our primary numbers we're going to be working with are constant, linear, quadratic, and cubic. Now, we could also classify a polynomial by the number of terms that we have. And so I'm going to kind of scroll back up here to the top, and we're going to talk about the number of terms of our polynomials. This first one, the f of x, has 3 terms. Our second one, g of x, has 1 term. Our third one, 4x minus 6, has 2 terms. And our last one, q of x, has 3 terms. So as we're looking at those terms, that's going to help us to qualify how many terms that we have. So let's kind of roll back down here. So we talk about a monomial. Let me give you some examples of some monomials. We could have 5. We could have 4x. We could have 3x squared. We could have 6ab cubed. We could have 18x, y, z to the 10th. All of those are monomials. Binomials. In terms of binomials, we could have 4x minus 1. We could have 6x squared plus 3y. We could have 2a squared b plus 18. We could have 9x minus 18b. Any one of those, in all cases, they have 2 terms. A trinomial, classically x squared plus 2x plus 1, which is factors. We could have 3x to the third plus x minus 6. We could have x to the 10th plus 2x squared y plus 9. Any one of those is a trinomial. So we can classify something both by degree as well as by the number of terms. So let's look at these 3 problems down here at the bottom. Let's classify them both by degree and by the number of terms. This first one has a degree of 5, and it is 1 term. So if we name it, we're going to call this a quintic monomial. Our second problem, we have a degree of 3 because it's 3, 1, and 0. And the degree is the highest number of the 3 terms. We also have 3 terms. So this is a cubic because of degree and trinomial because of the number of terms. Our last one in example 3 that we're looking at has degree 1 or 0. Let's think about this. Is this a degree of 1 or 0? Well, the exponent, had we written 1, would be an x to the 0. So the degree is 0. And it has 1 term. So this is a constant monomial. So, in review of our first page, our focus is on what degree, is it a polynomial, and how many terms does it have. Let's look at our second page. In your notes, you have some ideas that refer back to page 311. And as we're looking back to page 311, I want to focus in on some ideas here that are going to allow us to see some general tendencies of some graphs. We have some graphs here, and the ideas that you're going to be focusing here on is the idea of smooth and continuous. And if a graph is smooth or continuous, it's going to be referred to as a polynomial. However, if a graph is not smooth and continuous, then we're going to have some other issues in terms of working through, and we're going to look at our bottom ones down here, and we're going to see that these graphs down here on the bottom are not smooth. In this first case, we definitely have a break, and so we've got to understand that break causes it not to be a polynomial function. And then here, this point part up here where we have what's called a cusp at the top is something that also is going to give us some issues in terms of not being a polynomial function. So, just as we're talking through those general ideas, we want to make sure that we understand what causes things to be a polynomial function, once again smooth and continuous, and what not is a polynomial function, which is holes, breaks, or things that we would call cusps, which is those little points that things would come to. So we have a couple examples that I've drawn down here, and we're going to kind of try to determine if they are or are not a function. And once again, I want you to focus on 2 words. Are they smooth? And second, are they continuous? Those are the 2 questions that you're going to have to ask yourself. So, question A, definitely not smooth. So it's not a polynomial because we have this break. We have an asymptote. Asymptote. An asymptote is something that the line approaches but it never touches. So it is not a polynomial function. B, yes, it's smooth and continuous. So it is. C, we have a hole and a break, so it's not. D, even though it has a number of squiggles, it is smooth and continuous, so yes, it is a function. Our next one over here, as we're looking at it, is it smooth and continuous? It sure looks like it is, so we're going to say yes, it is. Our last one down here at the bottom is a little bit more careful. This is an absolute value function. You may remember from Algebra 1, this is the equation y equals the absolute value of x. However, because of this point down here, that's a cusp, and so this is not a polynomial function because it has a cusp down there at the bottom. Let's move on to our next page. We're now going to look at 6 graphs on our graphing calculator, and we're going to need to take a break on it as you're watching this recording to graph each of these. I've graphed these ahead of time, and so as we look at our first graph of y equals 0.5 x to the fourth plus 0.5 x to the third plus minus 3x squared, our graph is going to have some very unique functions. First of all the way out here in between 10 and 11 on the negative side, the graph is going to come down right between 10 and 11. Then the graph is going to go way down into the hundreds, and it's going to come back up, and it's going to cross through the graph right about at 0, and then it's going to shoot way up high. So that is what our graph of the first one is. Now realize this number down here is extremely low when I zoomed in on my graph. Okay, so that is a very, very low number, which is very difficult to draw here. But our points where it crosses the x-axis are going to be right here and right there. So it looks like it has 2 spaces where it crosses the x-axis. Our second graph that we're going to be looking at is the graph of negative 3x to the fourth plus 6x squared. Now, some different factors here is we have a negative as we start out our graph, and that's actually going to cause our graph to start down low. And our graph is going to come up, and it's going to approach the x-axis right at -1. It's going to touch it and then go back down. Then it's going to circle back here, come back up, touch it +1, but not go through, and then shoot back down. Kind of looks like an M. Don't forget your arrows. Once again, there's more off the graph than there is on the graph. Now I'm going to highlight my certain points here that are special. -1, +1, and the intercept is at -3, because our constant, our y-intercept still, is the back number on our graph. Let's look at the next one. Our graph here is a power of 6, and it's positive. Do you think you can make any predictions there as to what you're going to have? Well, a positive graph always starts up. And as a result, we're going to start way up, and we're going to go down, and we're going to come down, and we're going to cross right about close to -4 as we're looking at our graph. And then that graph goes extremely far down. Way, way far down. Then it comes back up, and it's going to come back up, and it's going to touch right at 0, 0, and go back down, and then shoot back up. Now, little mistake there on my part. I'm sorry about that. Let me correct that, because it doesn't go at 0, 0, but it does go at -1. So we're going to come up, we're going to touch at 0, we're going to touch at -1, okay, and we're going to come back down, and it's going to come back up right about at 1. And we're going to talk more about those zeros later on our last page of our graphs as we're working through. As we look at our next ones, We're going to try to keep graphing on our calculators, and this is a great chance for you to really experiment a little bit with your graphing calculators and work with the different functions and the exponents and things like that, and using the zoom function. Just a reminder, always you want to start by going to zoom standard and then zoom square, which will keep your graph looking as it best possibly can. On our fourth graph, we have an x to the fifth that's a positive. Now, from what you've remembered so far, possibly you might realize that this graph starts up where it starts down. Well, positive graphs that are of an odd nature start down. So this graph is going to start down and go through at -1, and then it's going to go up a little bit, come back down through, because you see we have a 0 y-intercept, and then it's going to kind of squiggle a little bit down here and cut back up in between 1 and 2 and shoot back up. So it starts down, it ends up, it's got kind of some funny looks on our graph. Actually, I think it goes up as I'm looking at my graph. I think it goes up a little bit more like that. So kind of some unusual graphs there as we're looking at them. Very rarely are you going to graph these kinds of things when they're in this form. We're going to use some other forms to graph them easier. Let's look at some keys here. We have an odd number, we have a negative number. So instead of starting down, it's going to start up. We have a 6 at the bottom, so it's going to 1, 2, 3, 4, 5, 6. That's going to be a key point as we look through. As we're circling down here, as you look at our graph, it crosses at -3, at -1, and at +2. So these are our points we're going to be shooting through. So -3 comes down, goes up, goes through 6, and then shoots back down through +2. And I was able to look at my graph and see all those different factors. So it's not really hard to differentiate there as you're looking through them. Our last graph, as we look at some different possibilities, the y-intercept is 0. So let's put a dot at 0. It's a positive and it's odd. What does that mean? That means it's going to start down. It also has a y-intercept, or an x-intercept, it looks like, at 3. So we're going to start down, we're going to make a little bump here, we're going to touch, we're going to shoot back up. And we're going to talk about the touching and shooting back up and what that means. That is a special thing called a multiplicity factor of 2 when it bounces back up versus going through multiplicity of 1, multiplicity of 2. But we're going to talk more about that as we move through our lesson. So, the direction that the graph is going as x is approaching positive infinity is going to be important. And then I forgot on here, that should be a negative sign right there. I'm sorry about that. So we look at what happens to the graph at the end of each of the two sides. And so is it going up or is it going down? And that's how we're going to represent that end behavior in terms of what we have. We might have a graph that's going up at the start and going down at the end. Or we might have a graph that's going down at the start and going up at the end. So any one of these multiple different 4 possibilities could be a factor as we're looking at those. So as we go back to our graphs, let's look at some of our behaviors. Our first one here was an even. Okay? That's an even. That's an even. That's an even. However, A and C are positive, and you notice A and C both start up. These 3 are all odd. Odd, odd, and odd in terms of our first numbers right there. A 3, and a 5. But 2 of them start down and 1 of them starts up. Which one starts up? The negative starts up. So we've got some possibility and some patterns there, hopefully, as you're discussing with your neighbors and your group. So let's try to write those down. If it's even and positive, it's going to start way up in the air. If it's even and negative, it's going to start down. If it's odd and positive, it's going to start down. If it's odd and negative, it's going to start up. Those are some ideas that we've kind of summarized there, and we're going to put them in a table as we look below. The number in front of the highest power is called the leading coefficient. And I think we've just talked about what that end behavior is and the sign of the leading coefficient in terms of what we're talking. If that leading coefficient is positive or negative, that's going to have to do with what's going on. So let's take a look and try to kind of summarize all of this in a chart. If it's odd, it's going to start down. And it's going to end up. All right? If it's even, and the leading coefficient, if it's odd and the leading coefficient is a negative, and I'm going to write a negative up here, I'm going to write a positive up here, then it's going to be the reverse of that. It's going to start up and it's going to end down. Okay, so let's write an equation here that might represent this. The simplest equation would just be something, f of x equals x cubed. And over here, f of x could equal negative x cubed. Very, very simple. So these two graphs are just going to start down and start up and make a little zigzag. So this equation is going to start up, the arrow is going to start down, it's going to make a squiggle through the 0 and then go back up. Over here it's going to start high, make a squiggle through the 0 and then head down low. So start low versus start high, it all has to do with if it's negative or if it's positive, and if it's odd or if it's even. So now let's look down at the end behavior of our even functions. Our even functions are going to start up and end up if it is a positive. They're going to start down and end down if it's a negative coefficient. So let's make some up here. G equals x squared. G of x equals x squared. I think you all know what x squared is. That's a parabola. So it's going to come down, it's going to touch, it's going to go back up. And notice it starts up and it ends up. We could make it a little bit more creative. We could have a function like g of x equals negative x to the fourth. X to the fourth is a w, so it's going to start up, going up from the bottom. It's going to make a w and go back down. So in each of those cases, we've got some issues with starting up and starting down, and it all has to do with the coefficient in front of the x squared, or the x to the fourth, and what the degree is on the function. As we look at problem 7, we're going to talk about the place where the graph crosses the x-axis. These places where it crosses the x-axis are called either roots, zeros, solutions, or x-intercepts. You may be familiar with many of these different terms that we've used over the years, but any one of these different terms means the same thing. It very simply means, where does the graph cross the x-axis? So I tried to highlight a number of these in number 4, but let's flip back to them and look at where they cross. On A, I highlighted those in blue. It looks like they cross in between negative 10 and at 0. So where does it? We have the x-intercepts are about at negative 10 and at 0. Let's look back at our next one. At B, it looks like it crosses at negative 1 and positive 1. At C, if you were to look back at C, a little bit harder to tell. It looks like it crosses over here at 1, 2, 3, -4. We know that was actually at -1 down there because of the y-intercept, and at +1. So -4 and +1 for C. Let's look at D. D looks like it crosses at -1 and at 0. E crosses at -3, -1, and +2. So -1 and 0, -3, -1, and +2. -1 and 0, -3, -1, and +2. So these are just called the x-intercepts, and you can tell those by looking at your graph. Our final one crosses at 0 and at 3 is what it looks like based on our graphs. Now these are estimates, realize, and the only way to get more accurate them is to use the zoom function of our graphs. Our last thing we're going to talk about is multiplicity, and how we have multiplicity based on our problems once we factor them. Multiplicity has to do with the number of times that a factor happens, very simply. And so if we were to factor things, here we have x plus, that's supposed to say x plus 1. Let's correct that, x plus 1 raised to the 5th power. So our factors are x plus 1 and x minus 5, but the multiplicity for x plus 1 is 5. The multiplicity for x minus 1 is 1. It has to do with the exponent on our problem. So let's look at our multiplicity of the problems that we've been working with this whole lesson. Our multiplicity here is 2. Multiplicity on x minus 2 is 1. And our multiplicity here is 1. Let's go through. No multiplicity on -3. Multiplicity is 2. Multiplicity is 2. Multiplicity is 5. Multiplicity is 1. Multiplicity on just the x is 1. On the x minus 2 is 3. On the x plus 1 is 1. On the minus x is 1. It's the exponents out here. That's really an exponent of 1, of 1, of 1, and of 1. So all of these have a multiplicity of 1. And our last one, multiplicity of 1 and multiplicity of 2. Now, when you look at the factored form, you start to be able to see what those numbers are had we been accurate in our graphs. And so if you were to solve each of these factors and set this factor like this x minus 2 equal to 0, you would get x equals 2 as a root. Or if you set this x plus 1 equal to 0, you would get x equals -1 as a root. Or over here, if you were to solve and do x minus 3 and do that, you would very simply get x equals 3 as a root. And so our multiplicity has to do with the roots and where they're going to cross the x-axis to make things a little bit easier for us. As we wrap up and talk about our graphs and thinking them, trying to make some generalizations about x-intercepts when the multiplicity is even versus the x-intercepts when the multiplicity is odd. Very simply, to kind of take you through here, whenever you have a multiplicity of 2, 2, 2, any kind of multiplicity that's an even number, that means that the graph is going to go up to the x-axis and it's going to kind of bump away. And so if this is the x-axis, the graph is going to come up to it and touch and go back away. Or it might come down to it and touch and go back away. So that's for even multiplicity. However, if you have odd multiplicity, the graph is going to go straight through the graph. So here, where we have this minus x, and this x minus 2, and x plus 1, and x plus 3, the graph is going to go through the graph at 4 different points. But over here on f, it's going to go through at x equals 0, but it's going to bounce at x equals -3. And so it's a very simple, quick way to sketch. So there's 0, 1, 2, 3, there's 3. Now, our total degree is 3. The system is all positive. So if we remember about degree 3, that means it starts low and ends high. And so very simply, at 0 it's going to go through, and then it's going to bounce back there. So let's kind of roll back all the way up to F, and let's see if that's what it looked like. And sure enough, here it is F. It has a downward tendency that's starting low. It bounces it at 3, and then it shoots back up. And so now that we've kind of got the whole piece put together, this allows us to really make predictions on what our graph is going to be. Now you're beginning to see maybe why factoring is going to be such a key idea in all of these. Once we can get things in a factored form, that's going to allow us to really see multiplicity. It's going to allow us to see degree. It's going to allow us to see if the function has a positive coefficient or a negative, so we can know tendencies if it starts up or it starts down. I hope this has been helpful. I know it's been kind of a long lesson, but I'm hoping it will be helpful as you review section 4.1.